All right, so today we're going to be taking a deep dive into this fascinating paper from Professor Yefimo's group at the University of Maryland.
Oh, yeah.
And they've been doing some really interesting work with super-ionic conductors, or SiCs as we all like to call them.
Yeah.
And specifically, they're looking at this concept of frustration, which plays a huge role in giving these materials their incredible conductivity.
Right.
But it's always been kind of a tricky thing to actually quantify, wouldn't you say?
Yeah, absolutely.
Well, that's where this paper comes in.
Yeah.
They've developed this really cool new tool called the density of atomistic states, or DOAS for short.
Yeah, I was looking over that and I was like, whoa, this is really cool.
Yeah, it is.
Yeah.
It basically gives us a way to actually visualize and quantify this frustration in a way that we've never been able to do before.
Yeah. How does it work? I'm really curious about that.
Well, SiCs are super important for all sorts of technologies, like all solid-state batteries and fuel cells,
Of
right?
course. Yeah.
And we're always looking for ways to improve their performance, to make them even more efficient.
Yeah.
But without a good understanding of this frustration,
Yeah.
it's kind of been like shooting in the dark,
Yeah.
Just kind of tweaking things and hoping for the best.
Just trial and error.
Exactly.
Yeah.
But with DOAS, we can actually see what's going on at the atomic level,
Mm-hmm.
which gives us a much better starting point for designing new and improved materials.
Okay, so walk me through this.
Okay, so they used I3YCl6 as their model system for this study,
Yeah.
which, as you know, undergoes a super-ionic transition at a certain temperature.
Uh-huh.
And DOAS basically takes snapshots of the lithium-ion configurations from molecular dynamics simulations at different temperatures, both before and after this transition.
Okay.
So it's giving us a picture of how the ions are behaving at the atomic level as the material goes through this transition from a low conductivity state to a high conductivity state. But how do they account for the energy changes associated with all these different configurations? That's the cool part. They statically relax each of those snapshots.
Oh, interesting.
So basically, they're isolating the energy changes that are due specifically to the ion configuration, filtering out all the thermal vibrations and stuff.
Oh, okay. So they're like subtracting out all the noise
Exactly.
to just get that pure signal.
Yep.
Nice.
And then they use those energy values to build a histogram.
Okay, histogram.
Yeah.
Makes sense.
So each peak on the histogram represents a distinct lithium-ion configuration, and the height of that peak tells us how often that configuration occurs in the simulation.
Gotcha.
But the really interesting thing is the width of those peaks.
The width.
Yeah,
What about it?
that's where the frustration comes in. So a narrow peak means that the ions are pretty much stuck in a single low-energy configuration. They're not really moving around much.
Okay.
But when you see a broad peak,
Ah.
that's when things get exciting.
That's where the magic happens.
Exactly.
Okay, I see.
Because it means there are lots of different accessible ion states, all with similar energies.
Uh-huh.
So the ions can easily hop between them without having to overcome a huge energy barrier.
Oh, that makes a lot of sense.
Yeah, it's like, if you think about a highway,
Uh-huh.
if you've got a highway with lots of lanes,
Yeah.
the traffic flows much more smoothly than if you only have one or two lanes, right?
Right.
It's the same idea here.
Yeah.
The broader the energy distribution, the more pathways the ions have for diffusion, and the higher the conductivity.
So it's like opening up new lanes on the highway for the ions to move around in.
Exactly.
Love that analogy.
Yeah. So did they see this broadening in the DOAS for Li3YCl6 after it transitions to the super-ionic state?
Well, that's what I was just about to ask.
Yeah, so they did.
It did.
They did. Before the transition, they saw two main peaks in the DOAS, which corresponds to the lithium ions neatly occupying those octahedral sites.
Like good little ions staying in their place.
Right. But then above the transition temperature, those peaks broadened significantly. And you start to see these new peaks emerging that represent the lithium ions occupying tetrahedral sites.
So the DOAS is literally showing us these ions getting more and more disordered as the material becomes super-ionic.
Exactly.
Wow.
And what's even more impressive is that they were able to directly correlate this broadening of the energy distribution with the decrease in the activation energy for ion conduction.
Oh, that's huge.
Yeah.
So it's not just a qualitative observation, it's actually a quantitative measure of how this frustration is directly affecting the material's performance.
Exactly.
Amazing.
So we've established that DOAS can visualize and quantify this frustration, but the real question is, can we use this knowledge to actually design better super-ionic conductors?
Yeah, that's the $64,000 question, isn't it?
Right, like how do we actually apply this?
Uh-huh.
Well, Professor Moore's group actually proposed 2 design strategies based on their DOAS findings.
Oh, wow.
So the first strategy is to introduce higher energy states into the material.
Higher energy states.
Yeah.
So you're essentially creating new accessible ion configurations with energies closer to those already activated states.
Exactly.
Okay.
It's like adding some strategically placed stepping stones across a stream. The
Ah.
ions now have more options for getting from one side to the other, and it takes less energy for them to do so.
Oh, I see.
And the second strategy is to broaden existing states.
Broaden existing states.
Yeah.
So you're making the energy levels of those existing ion configurations overlap more.
Yep, which again reduces the energy barriers for ion hopping.
Interesting.
So it's kind of like smoothing out the energy landscape,
I see.
making it easier for the ions to move around.
Yeah, so the ions aren't getting stuck in those depth energy valleys anymore.
Exactly.
That's a cool way to think about it.
And they actually tested out these strategies too.
Oh, really?
Yeah, they did some modifications to Li3YCl6.
Mm-hmm.
So first they looked at a different polymorph of the material with a slightly modified conjugation sublattice.
Yeah.
And this modification actually introduced new, higher energy octahedral lithium states,
Right.
as confirmed by the DOAS.
Oh, so they saw it right there in the DOAS.
Yep.
Neat.
And guess what?
What?
It improved the conductivity.
It did.
Yeah.
Wow.
They observed a lower transition temperature and a higher ionic conductivity compared to the original I-3YCl6.
So they were actually able to implement that first strategy of introducing higher energy states, and it worked.
Yep, it worked.
Like, pretty amazing.
And for the second strategy, they tried substituting some of the chlorine ions with bromine.
Oh, a mixed anion substitution.
Exactly.
Okay.
And that broadened those existing octahedral lithium states, again resulting in lower energy barriers for ion hopping. And guess what? That also led to improved conductivity.
I bet it did.
It did.
That's awesome.
So they've basically provided us with a roadmap for engineering super-ionic conductors with enhanced properties.
Wow, this is really groundbreaking stuff.
Yeah, no, it's pretty exciting.
Yeah, it is.
We've gone from just kind of fumbling around in the dark to having this really powerful tool that can actually help us design these materials with a much deeper understanding of how they work.
And it all boils down to being able to see this frustration and actually quantify it using DOAS.
Yeah, DOAS is a game changer.
It really is.
This is going to have huge implications for materials design in this field and probably beyond.
Absolutely. I'm already thinking about all the other materials we could apply this to.
Yeah, we do.
There's so much potential here.
It's mind-blowing.
Yeah.
So we've seen how DOAS can visualize and quantify this frustration and how we can even manipulate it to improve conductivity. But I think it would be really interesting to dig a little deeper into the specific insights that DOAS has provided into the mechanisms of frustration and disorder in these materials.
Yeah, definitely. Let's unpack that a bit more. So, we were talking about how insightful DOAS is and how it helps us visualize these energy landscapes.
Yeah, it's like we finally have this tool that lets us really understand what's going on with these super-ionic conductors at the atomic level.
Totally. And we were about to get into some of the specifics of what DOAS has revealed about how this frustration actually works during the super-ionic transition.
Right. Like, how does it actually play out?
So let's go back to our good friend Li3YCl6.
Yeah.
Our model system. Remember before the super-ionic transition?
Yeah.
The DOAS shows us those two nice, distinct peaks.
Right.
Representing the lithium ions in those octahedral sites.
The octali.
The octali, yeah.
All organized and behaving themselves.
Exactly. Just chilling in their designated spots. But then as the temperature starts to crank up, those peaks in the DOAS, they start to broaden like crazy.
Oh, wow. Here we go.
And that's telling us that the lithium ions are breaking free.
Yeah.
They're no longer confined to those octahedral sites. They're starting to explore other positions within the crystal structure.
They're getting adventurous.
Right, including those tetrahedral sites.
The tetla.
The tetlae.
Yeah.
And what's really cool is that DOAS doesn't just show us these new tetlae states emerging. It also tells us about their energy levels.
Oh, that's right. It gives us that whole picture.
And that's the key here, because those tetlae states, they have energies that are very close to the broadened octli states.
Oh, so they're almost at the same level?
Almost, yeah. And this close proximity in energy levels is super important for understanding why this transition to a super-ionic state happens.
Because it means that the energy barrier for those ions to hop between those octahedral and tetrahedral sites becomes much smaller.
Exactly, much smaller.
So it's easier for them to move around.
Way easier. And what's even cooler is that DOAS is basically giving us a visual representation of why this frustration actually enhances diffusion.
Right, it's not just about being disordered, it's that the disorder actually creates all these low-energy pathways.
Yeah, and that's the thing people sometimes get confused about. They think, oh, disorder, that must be bad, but in this case, it's actually good.
It's like controlled chaos.
Exactly.
Like, instead of being trapped in those deep energy valleys, those ions now have access to a more level playing field.
Exactly, and this isn't just some theoretical idea. It has real-world implications for how we design these super-ionic conductors.
Oh, right, like those two strategies we talked about.
Exactly, introducing higher energy states and broadening existing ones.
Yeah.
DOAS is basically letting us see how those modifications actually impact the energy landscape.
We're like landscape architects.
That's a great way to put it. We're shaping the energy landscape to create smoother paths for those ions to flow.
Very cool. So DOAS seems super powerful, but I'm wondering, can it be applied to other types of super-ionic conductors besides just Li3YCl6?
Totally. DOAS is a general tool.
Oh, nice.
It can be applied to any super-ionic conductor where this frustration is playing a role in conductivity. Professor Mo's group even suggested that DOAS could be useful for studying other classes of materials like metallic glasses or phase change materials.
So it's got a wide range of applications.
Yeah, it's pretty versatile.
That's exciting. So we've come a long way. We've gone from understanding this fundamental mechanism of super-ionic conductivity to actually being able to design these materials with incredible precision.
It's really remarkable.
And DOAS has played a huge role in that.
For sure, it's a game changer.
But before we get too carried away, I think it's important to step back and think about some of the broader implications of all this.
Yeah, that's a good point.
Like, what does DOAS mean for the future of materials, science, research, and development?
Big picture stuff.
Exactly.
Let's save that for the final part of our deep dive.
Sounds good. Stay with us.
Yeah.
We've really been digging into this DOAS method and how it's changing the way we think about super-ionic conductors.
Yeah, it's really impressive how much insight it provides.
I mean, it's one thing to have a vague concept of frustration in these materials.
Yeah.
But with DOAS, we can actually see it,
Right, and quantify it.
quantify it, and then actually use that knowledge to make better material.
That's the key, right?
Yeah.
We're not just observing it anymore. We're actually in control.
We're controlling it.
Yeah, like we're moving from this trial and error approach, which, let's be honest, has been the norm in material science for a long time,
Yeah.
to something much more rational.
More predictive.
Exactly. A predictive approach guided by these powerful computational tools like DOAS.
It's like we're designing materials from the bottom up now.
Yeah, like we can actually tailor their properties for specific application.
With way more precision than we could before.
And think about the possibilities
Oh, yeah.
for energy storage.
Right.
We could have solid-state batteries with much higher energy density.
They charge faster.
That charge way faster.
And last longer.
Exactly. And fuel cells, too.
Mm-hmm.
We could make them more efficient, more durable.
It's huge.
It's not just energy, though.
It's a pretty incredible time to be working in material science.
It really is, and DOAS is just the beginning.
There's so much more to come.
Yeah, we're at the forefront of this new era of discovery.
Driven by computation.
Like theory.
It's all coming together.
And it's going to take a new generation of scientists and engineers to really push the boundaries.
Absolutely. People who are ready to challenge those old assumptions.
People who aren't afraid to explore the unknown.
Yeah, to all those aspiring materials scientists out there, I say, embrace tools like DOAS.
Yeah, learn how to use them.
And use that knowledge to make a real difference.
The future is yours.
And it's looking pretty bright.
Thanks to these incredible advancements.
That's a great note to end on. This has been a truly insightful deep dive into super-ionic conductors and the DOAS method.
Thanks for joining us.
We'll see you next time.